All right, so thanks to coming to the session today, Scaling to Your First 10 Million Users. My name is Brett Holman. I'm a manager of solutions architecture at Amazon Web Services. You should be here to learn more about scaling on AWS. We're going to talk about scaling, fault tolerance, and how to scale your app kind of throughout the life cycle of the first user all the way to the 10 millionth and beyond. So that is the session for today. We'll go through a broad range of steps your application will make on that journey. So how do you start off scaling? And there's lots of documentation out there, how-tos, guides, topics, people with opinions, all of that. And where a lot of people are going to start, they're going to start with a search engine. That's pretty common. That's where I'm going to start. I'm probably going to do a search on Google for something I want to learn about. And as you see, you're going to get about 500,000 plus topics back. So it's a lot of things to read. So is that a good place to start? I would say probably not. This isn't where you want to start here. Unfortunately, we didn't get the best result, which shows us exactly a how-to guide on scaling your application. Auto-scaling, which is mentioned here on the overhead, this is actually a destination. It's a tool we may use, or we are going to use later in the discussion today, but it's not the end-all, be-all. It's not where you start from. So, I think, let's talk about where we do start first. Where do we start when we want to build an app out day one? And first, I want to do some level setting so everybody's on the same page. We're going to go through some basics, and then we'll dive into your day one application on AWS. So first off, AWS has 11 regions around the world. 5 continents are covered. We got regions in US West, US East, US West Oregon. We have an ITAR compliant region called GovCloud in the US for ITAR compliant workloads. There's also 2 regions in Europe, a few in Asia, Australia, South America, Brazil. So a region is like an island. You can think of it as a place where we have multiple data centers in more or less a metropolitan area. And so it's going to be many data centers. And each one of those regions, when you actually put your data into a region, your data stays in that region. I mean, you can always move it, you can copy it, but it's not going to move outside of that geographic area without you knowing about it. You have control. So regions are made of availability zones. So I mentioned data centers. I didn't want to mention availability zones until I kind of defined what it is. But essentially, an availability zone is a data center or a cluster of data centers on a piece of property like a campus environment. So in some cases, we've outgrown that single data center in one piece of property. We've grown out to 2 or 3 or more on a single piece of property. So an availability zone is a cluster of data centers on a piece of property, and every region has 2 or more, oftentimes 3 or more availability zones. Each one of these availability zones is built to be fault tolerant from each other. So they're on different power grids, floodplains. So they have different tier 1 internet service providers, multiple of those. There's multiple routes of fiber between the availability zones in the region. It's low latency. You're looking at low single-digit millisecond ping times for latency between availability zones. So, in the end, we're going to talk much more about this today, but you can actually build apps that span regions, or a single region. So your app lives within a single region. We're going to talk more about that in the coming slides. So. Lastly, on the kind of the geography side, we have over 50 edge locations around the world. It's constantly growing. We're constantly adding new edge locations to get closer to our customers, where people are putting the most demand and so on. Essentially, these represent our CDN or our route, which is CloudFront, our content delivery network called CloudFront, or our DNS service called Route 53. And these are geographic services. If you want to do a DNS resolution, you're going to end up at the closest POP on this edge location map. Same with content delivery. If you're actually delivering content via your application to a user and you're using our CDN, CloudFront, you'll go to the nearest POP on this map. So what do you need to build an application on AWS or in general, just in your own data center? First off, you need your data center, right? You need your place where you're going to your physical footprint where you're going to put all of your other services in place. So you need your data centers. You need your foundational services like your compute, storage, and networking. Then you've got your platform and application services, things like email, queuing, messaging, orchestration, deployment tools, monitoring. All those things are required. And we have services in each one of these areas that actually fit your particular needs. Lots of things at the platform and application level. So if you look down at the bottom, Infrastructure is what we just talked about. It's those regions, availability zones, and points of presence on our CDN network. Foundational services, infrastructure as a service, what we're very famous for, compute, storage, networking. You also have a bunch of controls for security and identity and access management, so you can control who has access to your AWS resources. We have a ton of platform services as well, things in the database space for relational databases, NoSQL, caching, analytics for like Hadoop, real-time analytics for streaming ingest, data warehousing, automated workflows, app services for queuing, orchestration, email, transcoding, you name it. We've got deployment services for deploying applications, for managing application lifecycle, template-based, building out of your infrastructure, monitoring, log tracking, all of that kind of stuff. And then lastly, we've got some mobile tools for mobile developers. And then at the very top in the application layer, we have our virtual desktops and collaboration and sharing services. So before we leave the overall services, I wanted to define a few things. I don't think this is said often enough, so I think it's something to note. We have services at the global level, at the regional level, and at the local level. And I want to tell you what I mean by that, and then we're going to use these concepts as we go through the talk. So first off, at the global level, we've got our CDN, CloudFront, and Route 53. Those things span the globe, nodes all over the place, over 50. Then, as you get down to the regional level, we've got a bunch of inherently fault-tolerant services that are self-healing, scaling, and all of that. Things like S3, our cloud object storage. So if you want to store an object up in S3, we replicate your data all the way around the region, multiple copies of it, so it's really durable. DynamoDB, when you do a write to our NoSQL DynamoDB platform, you're writing to multiple AZs before you get a commit. So highly durable again. Elastic load balancing, you can actually load balance traffic to multiple availability zones, to servers running in multiple availability zones on AWS. So the load balancer is scalable, it's fault tolerant, and it can spread traffic all the way through the region. And lastly, SQS, it's our messaging service. If you want to, you can always build out your own messaging service on EC2, but you can also use ours, and it's fault tolerant. It's meant to scale with you, so you don't have to worry about scaling it, worrying about building a fault tolerant service. SQS is just there. You can just put messages in there and get messages out. So lastly, the last concept here is things that are local to an availability zone, things like EC2. If you actually go and turn up a virtual server in the cloud, it is on a physical piece of hardware somewhere. There is a host somewhere that's running that particular virtual server, and if that virtual server goes down, that server's down. Right? It's not fault tolerant by default, but by building out an architecture with a load balancer in front of it and spreading traffic across a tier of servers with our load balancing service, you can health check the server, remove it from processing requests, no longer send traffic to it, and you actually have a little fault tolerant architecture with our load balancer and a couple EC2 instances. So we're going to talk more about that as the talk goes on. So let's start out day one, user one, which is probably you, the developer that's building out this application. So this is probably what your architecture looks like in its most basic form. You've got an EC2 instance, which is basically your server in the cloud, and you're running your web and apps, or your web server there, your database server there, any management tools, all that stuff is running on that single host, or that single virtual server, and then you're attaching an elastic IP to it. Then you're going to go create a DNS entry that maps your domain name to that IP address, an A record that maps that domain name to the IP address that you assigned to that EC2 instance, and now your users can get to that particular instance via Route 53 DNS lookup. So this is kind of where you start, and we can get pretty far here, but scaling isn't, it's not forever here. There is one option though, there's vertical scaling. So let's say we started off on a smaller server instance, we can always go to a bigger box. This is the simplest approach to scaling. Really easy to edit a server. So let's say I want to move from a small server to a large server. I can just stop the server, edit the instance type, change it to a larger instance type, and reboot it. A couple minutes later, I've got a bigger server running with the same IP address, the same storage, and all of that. So there are a whole host of different instance types. We group them in what we call instance families. So an instance family would be like the compute-optimized instances, the C3s and C4s. The high-IO optimized instances, which would be the I2s, or the memory-optimized instances, the R3s, or the linear compute and RAM instances, which are the M3s. And essentially what you want to do, you want to take a look at your workload. You want to look at the metrics and see where it maxes out. Does it max out on CPU? Does it max out on memory? Or is it pretty linear Or is it I/O that is the thing that limits my workload? And then you pick a family for your EC2 instance that follows where you're limited. What metric do you max out on first? And then inside of an instance family, you got instance sizes, right? So you can, there's the T2 micro, like we show in the bottom of this. There's also the C38XL. So there's graduations in each family of different instance sizes that have more horsepower. So also we can leverage EBS optimized instances, which optimize our access over network to storage, and you can actually do provisioned I/O for your storage as well. So you can say, hey, I need a really big drive of this size, and I want 10,000 IOPS or 20,000 IOPS, and you can do that as well. So, so this is kind of our first spot in terms of scaling. You're going to eventually hit an endpoint, though, right? This is only going to go so far. You're not going to be running a web scale app on one server, I hope. So, we can potentially get to a few hundred users, maybe even a few thousand, depending upon our app complexity. But we don't have any failover. We don't have any redundancy. We've got a lot of eggs in one basket here. Not necessarily the best architecture. But maybe dev or maybe standing up our initial POC or our MVP that we're putting out there, this might be the way we do it. I would suggest there are probably some better architectures, but nevertheless, this might be the way a lot of people do it. So let's talk about day 2. We're still at user 1 or greater than 1. So what's the first thing we can do to make our app a little bit better? Well, first, we can break apart the database and the web app. I mean, that's just a basic thing, right? So here we've done just that. We've actually separated the database instance from the web instance. And now what can we do? We can actually scale those independently at each tier. Now we can vertically scale each one of those instances, so we can go twice the size. And we might find that our database scales much quicker, needs to scale much quicker than our app, or vice versa, right? And we might find out that we want a memory-optimized instance for our database server, or a I/O-optimized instance for our database server, and we want a CPU-optimized instance for our web. So anyway, this is our first starting point. So what are our database options if we're going to break out the database now? First off, you can run any database on EC2, just about any database on EC2. You can go and install it, bring your own license. If you're a DBA and you're comfortable snapshotting, doing backups, patch management, if you need to make it high availability and cluster it, doing all of those types of things, this might be for you. This also could be for you. Let's say you've got something very unique you're trying to do, and you really need to work with the hardware and have access to the hardware on the database instance. This might be the right place for you as well. And also if you don't have, if one of our other solutions doesn't accommodate you. But we think there are some better options out there, and RDS would potentially be one of those, right? RDS is our relational database service. So it's Postgres, MySQL, SQL Server, and Oracle. And we manage it for you, so it's database as a service. We launch it kind of with a general standard default config that's good for that particular database. And you can change the sizes you want, just like you could a server. You can also scale the storage. You can say, I want to go from 100 gigs to 200 gigs. You can also cluster it, high availability, set up snapshot management and patch management. We take care of it all for you. You just set it up on a schedule. So it's a really great service to get started with. And lastly, I talked about the high availability clustering. You can also do read replicas with Postgres and MySQL, so that's a pretty powerful tool as well. DynamoDB is our managed NoSQL offering. It's SSD backed. We call it zero admin because there's really just a crank. You just kind of say, hey, I want this many reads and writes per second, and that's all you really crank, and we auto scale it on the back end based upon the size of the database, or the size of the table, I should say, and how many reads and writes per second you're trying to do. So if you've ever heard of the Dynamo white paper back in 2003, this is really that was kind of the grandfather of a lot of NoSQL engines like Cassandra. It was written by Amazon back in 2003. Well, this is kind of the evolution of that. This would be like the cousin, 3 generations later or something like that. Redshift is our petabyte scale data warehouse. Fast, powerful. You can start off with one node, scale it to many nodes. You speak to it with ANSI SQL over the wire. It's really great in terms of price performance as well. So you can start off really small on a single node, but it's massively parallel. You can scale up to 100 nodes. So your workload might only require one small node to start, but you might go to, like 108 XL nodes to finish, and you might be running at petabyte scale on this data warehouse. So, it comes in at a fraction of the cost of a lot of the other database or data warehouse engines out there. So how do you choose which technology to start with here? Do you want to start with SQL, NoSQL? Is data warehouse right to start? Probably not. Unless you're just doing an analytical tool. Some people aren't going to like this, but you should start with a SQL database. I mean, every application has a SQL database somewhere in their architecture. I mean, for the most part, and pretty much everything you see out there today has that. So SQL's a great place to start. It's established and it's a well-worn technology. There's lots of existing code, books, tutorials, how-tos. Lots of people, most importantly, right? Lots of people know SQL. Probably the majority of people in the room do. So when you're trying to hire people, it's pretty easy to hire people that know SQL. If you go to NoSQL, how many people are running at scale and really know how to do that really well? I mean, it's a much smaller number. You're probably not going to break SQL in your first 10 million users either. And there's a little asterisk on that. You know, you might be doing something weird or have massive rapid ingest, and there might be a case for NoSQL, but chances are most people aren't going to break SQL in their first 10 million users. And we're going to talk about the clear patterns to scalability for SQL databases as well today, and NoSQL as well, but you know, later in the talk. But you know, there are clear patterns to scalability that people know how to execute. So you said massive amounts of data. Well, you might be thinking, I have massive amounts of data, and maybe there's a couple of you that do. But let's clarify what massive amounts of data means. You know, if your usage is such that you're bringing in several terabytes of data in your first year, or you have an incredibly data-intensive workload, like thousands of transactions per second coming in, or thousands of writes per second, or many thousands of writes per second, maybe then, you know, this is right for you. Maybe NoSQL is right for you. And we're going to talk about some of the use cases for NoSQL later. But you know, I mean, there's a few other use cases: super low latency applications, metadata-driven data sets, highly non-relational data that doesn't store well in a schema, things that require schemaless data constructs. And the asterisk there, not just because the developers are lazy and don't want to define a schema. It's pretty easy to define a schema, and relational databases are easy to use. So you know, that's not a good excuse. Again, massive amounts of data or stuff that's got rapid ingest. So now we're getting up to over 100 users. We separated our tiers, our web and app tier. We're going to use RDS now for our database of choice, and we're going to use MySQL in this particular scenario because AWS is going to manage it for us. We just need to manage the tables, the indexing, the kind of the standard stuff around tuning, but not necessarily the hardware, the snapshotting, and all the other things that aren't a huge value add for most applications, because AWS can take care of those on the backside. So as we start scaling up to over 1,000 users, we want to start talking about and thinking about our fault tolerance, our lack of failure, or lack of failover, our redundancy issues. So first thing we're going to do, we're going to get rid of that elastic IP. We're going to go create an elastic load balancer, and with Route 53, we can create an alias record that points directly, the whole domain directly at the ELB. Or we can do a CNAME to a particular subdomain. And then behind that ELB, we're going to put a couple web instances in different availability zones. Right now, we can spread traffic to multiple availability zones. And you know, Werner Vogel's AWS CTO always says everything fails. When you're talking about hardware, software, everything fails. So build things that are fault tolerant by nature, right? At every tier of your application. That's a really common thing he says in a lot of his talks. So you know, ELB is self-healing on its own, and it scales organically. And now our web instances, ELB also health checks our instances. So now we'll serve traffic to two instances. If one of them goes down, we still got another. And then lastly, we've got a clustered, when I say clustered, we've got a high availability database for MySQL. We've got a master and we've got a slave, and we're synchronously replicating to the slave as we write to the master. So if that master goes down, we'll automatically fail over to the slave. Your application will use the same connection string. You don't have to write any logic around that. As the DNS fails over and the master is up, you can automatically start hitting the master as soon as it's up. Small little amount of downtime. And then we'll start spinning up another slave in another availability zone. So we've got a high availability or a pretty well architected application here for our 1,000 users, or a little over 1,000 users. So let's quickly talk about what elastic load balancing is. So it's a highly scalable, self-healing load balancing service that can distribute load across multiple availability zones to multiple EC2 instances. It does health checks. That's really key. You can set up a health check on your particular web or app tier or whatever, and then the load balancer will go check it, and you can set up the interval how often it checks it. And if it fails, you can actually fail it out of the tier. And you can make that a really deep health check that hits your database, or it can be a really simple health check that just says, yeah, the web server's up 200 OK. You know, so pretty powerful there. It also supports Ssl termination, so you can terminate all your SSL on the load balancer, not on your servers. Take that load off of the servers. It also supports sticky sessions. So if you've got your session state stored on your server, You can actually make sure that the load balancer will direct your user to the same server every time. And it publishes metrics to CloudWatch, so you can actually track what it's doing. You can actually push logs out to S3 as well. So yeah, so use ELB. So we can get pretty far scaling horizontally and vertically with this pattern that we got here, tens to hundreds of thousands of users. And this is what it looks like, right? We've got about 8 web instances here, and we've got a master database replicating to a slave database, and we've got a series of read replicas in each availability zone, and we're doing all of our reads against the read replicas to take that weight off of the master. So we're only writing to the master, but reading from these read replicas. Now, we do this as a service. We'll stand at these read replicas. They're not synchronously replicated to. They use MySQL replication, so they can be a hair behind. So if you need to do a consistent read, you might need to do it against the master. But things that are typical that you can read out of the database, you can read out of those read replicas. And typically, if you don't have a super write-heavy application, it should be pretty close to in sync. So this is going to take us pretty far, but we do care about performance and efficiency. We kind of have a monolith here that we've built out. So we're going to talk about some ways to start separating out some things and shifting some things around. So let's start shifting some things around. We want to lighten our load on the database and lighten our load on the web tier. So the first thing we can do is move some static content out of the web servers and move it out to S3 and CloudFront. So we're going to talk about that in a little bit. And then we'll talk about moving session state and standard common queries out to cache. So first off, all of your JavaScript, your CSS, your images, your videos, all that stuff that's static, that's sitting on your web servers, imagine if you're getting thousands of hits, or hundreds of hits a second, and you're serving up video or images, and every time you get hit, you're serving up that heavy content. You don't have to have that content on your web server. That's something that works really well in S3. S3 can be the origin for your static content, and you can further put CloudFront, our global CDN, in front of it, so you've got that content cached close to the users all over the globe, and you deliver it from a very close location, helps increase your response time to your users, and takes that load off of your web servers. So it's a really common pattern used by many of our customers. So what is S3? Well, it's a cloud object storage. So you can store objects up in S3, and you can reference those objects with a RESTful URL. And the object you store in S3, you can have very tight, fine-grained security permissions about who can get to that object, with a particular credential, or you can make it public. So that's what we want here for this public web app that we're talking about, right? But yeah, that's a very common pattern, right? And then 11 nines of durability. What does that mean? Well, it means every time I put an object in S3, we're replicating it around the region. Remember I said the data doesn't leave the region? Well, it doesn't. You've got 11 nines of durability, meaning that that object's highly durable. There's a checksum placed on it. If one of the objects degrades, we'll actually blow it away. And you're only going to be served up a good object. So this is great again for things like JavaScript, CSS, images, videos, backups, logs. A lot of people centralize their logs to S3. Common place for Hadoop to read out of, or our data warehouse to ingest from. So S3 is common for a lot of things. And further, you can put our CloudFront in front of it and actually have the global caching in front of it. So probably the last thing to note is that it's a good logging endpoint for all the different services. So a good place to dump your CloudFront logs, to dump your ELB logs, and to do introspection on your application as well. And further, you can actually tier off your data. So there's a Glacier archival service, which comes in at about $0.01 a gig per month in most regions. And you can say, hey, all this log data, after 30 days, I want to just put it out in our archival location and pay $0.01 a gig versus whatever I'm paying in S3. So CloudFront is that global caching capability for that content. We can cache static content all over the globe close to the user. One of the things it also does, though, it can be put in front of your site as a proxy back to your dynamic origin, back to your web stack. So you can actually have your web stack behind CloudFront and have a local CloudFront node proxy the connection back. And it actually accelerates that connection, so it actually speeds up the response time for dynamic content as well. And it's great for streaming video, lots of other technologies. It supports a 0 TTL, so when we talk about that dynamic content, we can set a 0 second time to live on that origin, that dynamic origin, such that we're always going to look back to the origin, to go fetch the dynamic content out of your web stack. We might set a high TTL over on the static content, like a day or 10 days or whatever, and keep that stuff cached out on the edge. Oh, actually, a couple things here. Upper right, response time. So it shows what a site, like what a representative site would be in terms of response time and server load with no CDN, with CDN for static content only, and CDN for static and dynamic content. And this is a particular example of one particular site. But you can see as you get to the far end, with static and dynamic content being cached by CloudFront, your server load and response time is at its best. So at the bottom, that's a representative example of a particular customer who is running, it looks like under about 5 gigabits per second on that particular graph. Pretty solid load, but all of a sudden they spiked up to 60 gigabits per second. Well, they had CloudFront in front of it, and didn't cause any alarms to go off or bells to ring because they had an architecture that responded to it, and CloudFront was proxying the majority of that traffic. So really, isolated their application from that massive spike of traffic. So next pattern here, moving session state and common queries out of your database. So why is it important to move session state? Because we're going to talk about scaling out our tiers next, and it's hard to scale out a tier when you have sticky sessions going to a particular server instance. Let's say I've got my servers pegged at 95% CPU, and I scale out and add 4 more servers. Can I move those users on those servers that are pegged out and getting slow response times to those new servers? No, I can't, right? Because the session state is being stored on the server. If I actually set up my servers as stateless and move my session state out to something like DynamoDB, as is in the architecture here, then my servers are stateless. I look up my session state information in DynamoDB, and I can scale out and scale down without worrying about losing session information for users. So it's a good pattern. Also, caching common queries in cache is another good pattern, and we're going to talk a little bit more about that as well. So this particular architecture shows those two things happening here. So we talked a little bit about DynamoDB, so I'm just going to touch on it. But again, it's our managed provision throughput NoSQL. Further, it has connectors from a lot of the SDKs to store session state automatically. So you just plug in the connector for like PHP or Java or what have you, and it'll automatically start taking that session state out of your app and pushing it out to DynamoDB tables. So pretty powerful. So you don't have to do a lot of heavy lifting to actually get that session state moved out of those tiers and make your tiers stateless, like we talked about. Fast, predictable, again, single dial to crank. It has support for JSON now, and it supports larger item sizes as well. So pretty powerful, and this is like a managed database. It can scale fairly infinitely. We've got examples of users that are running at 500,000 reads and writes per second. Imagine what you got to scale out in terms of infrastructure and management to do that, and this is zero admin. So Elasticache, this is our hosted memcached and Redis service. Thing to note here is it really speaks the same API as standard memcached and Redis, the open source tools. So, but we handle managing the cluster for you. We allow you to scale out nodes or self-healing, and this again gives you very fast low single-digit millisecond response times from queries. So there's a good place for cache in there for caching common queries and taking that load off your database. So wanted to quickly talk about a caching pattern here. What would you do if you wanted to start caching common queries? How would you make that work? If you've heard the lazy load pattern, that's a good, you can pre-warm your cache by loading it all up with, these common things you look up. But you can also just say, hey, I'm going to go look in the cache. My application is going to look in the cache. If it finds the value I'm looking for, I return it, and my application uses it for processing. If I don't have it in the cache, I go to the database, look it up, put it in the cache, and then return it to the application. And the next time, and I can set a TTL on that value as well. Time to live, excuse me. And I might say, this is good for 10 seconds, or this is good for 10 minutes, or whatever it makes sense for that particular piece of data, right? But now, let's say I'm hitting that same value 10 times per second. I'm taking a lot of load off my database, and the cache is very fast to respond. So use caching to take load off your database for your common queries. And lastly, move your dynamic content out to CloudFront. Put CloudFront in front of your Elastic Load Balancer in your web stack. And again, it's going to proxy the connections and accelerate that connectivity back to your origin. So you're going to get better response time for your pages that you're rendering, as well as lower server load, allowing you to shrink that web and app tier. And that's probably what costs most in your application stack. So we're in a spot now where our application is much more lightweight than where we started. So if you think about the beginning of our talk, we had everything, boxed in there, but we still have a pretty monolithic application, right? I mean, This thing is a monolith. All the business logic lives on those web servers. Nothing's really separated out. We did remove static content. We did remove some caching on the database side, but we're gonna go a little further here. But first, we're gonna talk about autoscaling, and we're gonna go back to the beginning of our talk. So autoscaling is the resizing of compute clusters on demand, right? So you can take a tier, like a web tier or an application tier, and you can scale it out horizontally or horizontally as well. And the way it works, you basically define a launch configuration, an autoscaling launch configuration, which says every time I launch a server, I want to launch it just like this. I'm going to use this image, this AMI. I'm going to use, this is the user data I might want to pass in, and this is the instance size I want to launch. And that's essentially what a launch configuration is. Then I go and define an autoscaling group, and you can see the autoscaling group down there. I want a min of 4 servers in my tier and a max of 200. And I want to be in these 2 availability zones, US West 2C and US West 2B. And then lastly, I define a policy, either a policy to scale by schedule or to scale by metric. And if I want to scale by metric, I use CloudWatch metrics, and I can say, hey, when my application tier is over 80% CPU for over 5 minutes, let's scale up by 2 instances or 4 instances or however many make sense, right? And if my application is cooling down and my CPU is below 40% for, say, 5 minutes or 10 minutes, I might shrink by 2 or 4 servers or whatever I want to do. Let's say I know there's a particular time of the day. I don't want to start scaling as the traffic's coming, but I know at 5 p.m. people get home from work, traffic doubles on my site. Maybe at 4:30 I double my fleet, right? So I can scale by schedule as well, and then I can scale down by schedule, just the same. So autoscaling has a place in your tier, especially where there's variability. So this is typical weekly traffic to Amazon.com. You can see the peaks during the day, the pits at night. And imagine where the provision capacity needs to be. To accommodate a spike, you need to be about 15% above those kind of typical peaks. So this would be our provision capacity. Well, imagine it's November, and you've got Black Friday and Cyber Monday, and your chart looks more like this. Where do I need to provision capacity to fulfill all these requests? I need to provision it somewhere up there, right? So I'm way above my normal usage. And if you think about traditional data center, 6 to 12 month planning cycle, right? I may have done this way before November, and way after November, I'm going to have all this extra capacity sitting there that's being unused. And according to this graph, 76% waste here. So wouldn't it be better to do something that was matching supply and demand like that, where you just are using a little more CPU than you need all the time? Well, that's what autoscaling lets you do. So that's why you want to use it. That's why you scale out tiers, and that's what Amazon does. That's what a whole host of AWS customers do that operate at web scale. So good tool to use. So now we've got this application. We're over 500,000 users, and we've got autoscaling web tier. We've got we're caching our content in front of our app with CloudFront. We've got static content coming out of S3, our dynamic content coming out of our load balancer. We're using master-slave databases with read replicas for the reads and all the common queries coming out of the cache. And we've got all of our session state in DynamoDB, right? And so we got a stateless tier we can scale out and scale down pretty easily and not worry about losing session data for users. So we're in a pretty good spot. But what's next? You probably don't want to be deploying all this stuff by hand. And this architecture is going to get a lot more complicated as this goes on. I mean, as we start talking about web scale, we're going to have a lot of moving pieces here. So, this is a good point to kind of move over to this topic of automation. So, use automation becomes really important. There's a whole bunch of tools inside of AWS to automate and make sure you're automating all the repetitive tasks and your release cycle or your processing, your software development and release cycle is very fine-tuned and you're repetitive. You're not doing things manually. There's a whole host of third-party tools out there for configuration management of instances and so on, things like Chef and Puppet and Ansible and many others. And then there's, make sure you instrument your application as well. Monitoring, metrics, logging, application performance monitoring. These things are all really important. There's a lot of great third-party tools out there. You don't have to reinvent the wheel. Take a look at them. So here are some of the AWS application management tools I'm going to quickly touch on. They kind of range from convenience to the most control. So Elastic Beanstalk, basically if I'm a developer, I don't want to worry about my infrastructure. I just want to write code and deploy it. and just kind of specify a few things in the GUI around what I want to scale from and to. Beanstalk's great. I just deploy with Git or with Eclipse, push my code to the application. Beanstalk will version it and deploy it to the instances, and you can even do blue-green deployments with this as well. Pretty cool for like a 2-tier app or a 3-tier app. Load balancer, tier, database. OpsWorks is an application lifecycle management tool. So what it allows you to do is you can write layers. So you can have a multi-layer app, a more complex app with many layers, and each one of those layers, you can use chef recipes to manage that layer. And out of the box, we've got many chef recipes defined for many standard layers like a Ruby app layer, or a PHP app layer, or a Java app layer, or a load balancing tier, or a database tier, or a management tier and monitoring tier. So there's all these layers you can just go use out of the box, but you can also write any of your own custom layers. You want to run Mongo, you can write a Mongo layer, right? Or whatever it might be. So OpsWorks allows you to do that and then orchestrate the overall application lifecycle from OpsWorks. So pretty cool. CloudFormation is infrastructure as code. So what that is it's a declarative resource-based tool, or language, I should say, where you can go out and script out all your resources for your application into a stack. And you can say, for my EC2 instance, I want to use this size, and I want to deploy this many in an auto-scaling group, and I want to use this AMI, and here's my bootstrap actions that I'm going to pass in via user data, and here's the security groups that are going to go on it. And you can define all the relationships, right? And then you can test deploying it, just like you test your application. You can test your infrastructure. You can version it as your application grows. It's a very powerful tool. Lots of control there. And then lastly, you can always manage everything on EC2 on your own. But that requires a lot of hands, and especially as we start getting to web scale, you're going to see that it would take an army to manage manually deploying these things. That would be very hard, and lots of risk there too. So as we start getting up to 500,000 users plus, we're going to start running into issues with speed and performance. So that's where a lot of these monitoring and metrics tools come into place. It's really important to instrument your application. Pay attention to what your application is telling you, and we're going to look at a couple dashboards coming up here. Also, pay attention to what your users are telling you. Talk to your super users. Find out who they are. Maybe send out a survey. Your users are going to know what works really well on the page and what doesn't. What areas of your site don't respond well, what don't load well, what crash, all that kind of stuff. So that's a good thing to do. And remember to try to squeeze as much performance out of each service or component as possible. So this is a couple just representative examples here. You got your host level metrics from CloudWatch. You got your aggregate level metrics from CloudWatch. What are they good for? Host level lets you drill into what's happening on a particular instance. If there's an instance in trouble, you can go drill into what's going on there. Is it maxed out in CPU? What's going on? Is it maxed out in I/O? Aggregate level metrics let you see what's happening on a tier for an application. You can also use CloudWatch logs to push all your logging to CloudWatch logs, and you can set up alarms and metrics that capture an event happening. Like, hey, if this event happens 5 times in some period, I want to know about it, right? And you can be watching for something in your logs that happens. You're like, oh, it alerts your admins or your ops people or whatever, or an action is performed, right? You take that alarm, send it out to a queue, and you have some agent that's actually pulling that queue and doing some action because of that. So lots of things you can do with CloudWatch logs and the metrics that come out of that and the alarming that comes out of that. Lastly, it's important to understand what's going on with your external site performance. Tools like Pingdom, which is in the bottom right corner here, will tell you, what your site's doing. Lastly, I don't have a picture of it, but like something like New Relic, AppDynamics, application performance management tools are really key. It allows you to drill into a particular, like a page render, and see what each controller is doing and what database calls are happening and how long everything takes at each step through processing that page. And you can say, oh, well, 2/3 of the time is spent right here in this controller and this database action here, and maybe I need an index, or maybe I need X or Y or Z. Obviously you can go to more advanced profiling tools, but this gives you a good aggregate view of what your application is doing. So I'd take a look at some of those tools as well as you start getting to this point. So there are a lot of further application or improvements to be made in breaking this application apart. We're kind of at the base here. We've got a web, an app layer that's running on the same server. All of our business logic is in one place. We basically got a monolith right now. So what can we do next? what does SOA mean? So I actually was looking for a good diagram for this particular slide, and this is what turned up in Google Images. I thought it was pretty funny. So it's not Sons of Anarchy. It's service-oriented architecture, excuse me. But I thought it was pretty good. So really what this is about is actually moving all of your services into different tiers and modules, and then treating each of these as 100% separate pieces of your infrastructure. So you're going to be able to scale them out independently of each other, so you can reach much greater scale that way. And AWS does this, Amazon.com does this. Hundreds of services are under the hood that represent what you guys see in a handful of services or a handful of pages, right? So think of Amazon.com, you've got recommendations going on, you've got a search bar, you've got user reviews, you've got all these things that plug into a page. Are those all part of a monolithic application, or do you think they're independent services running behind the scenes that are scaling on their own? It's going to be the latter. So I think this is actually a good demonstration of something I was getting to earlier when I was talking about those self-scaling, fault-tolerant services. Loose coupling plus service-oriented architecture really equals winning, especially when you combine it with services that are available out of the box that you can use today that will scale for you. Don't have to worry about it. You don't have to manage them. You don't have to worry about them being fault-tolerant. They're fault-tolerant by default. So there's lots of examples in that platform and application tier that you can use to fit components of your architecture, like, hey, we need to send transactional emails and we want them highly deliverable. Well, you can use simple email service. Hey, we want to decouple our application and put queuing in between tiers. Simple queuing service. Simple notification service for pub-sub messaging. And lots of examples here, orchestration, Lambda. And we're going to talk about simple queuing service and Lambda coming up here. So what is simple queuing service? It's really a reliable, scalable queuing service for storing messages as they travel between your application tiers or between your instances, right? There's simple APIs to put messages and to get messages. There's SDKs for all the major languages. So it's really easy to just do a put into a queue. I typically put a JSON message into a queue in a particular structure, and then my receiving instance knows how to read that JSON as well, right? And the get out of a queue is very easy as well. Just plug in the SDKs for any of the major languages. It can scale unlimited number of messages, so it's great to use. Little example here in the upper right. Let's say we had a photo CMS. So I've got a big photo CMS. I've got users uploading thousands or millions of images, every week. And do I process those on the web instance? This would be a great example of decoupling, right? I probably don't want to create 10 different copies of that image in different sizes for different form factors on my web instance. What I want to do is I want to just go store that back in S3. I want to put a message in the queue, and I want to have something on the back end asynchronously out of the synchronous flow of my user uploading that image, go and create the 10 different copies. So I put the message in the queue to do the rendering or create all the different images, and then I've got a back-end instance that can, or tier of instances that can auto-scale based upon queue depth to do all that work on the backside. So, and I can actually set up auto-scale methods that happen off of queue depth in SQS. So I can say, hey, if my queue depth is X, scale up. So another pretty cool service that we released into GA, I think today, if I'm not mistaken, is Lambda. It's an event-driven compute. They're calling this the connective tissue for AWS services. It's a good way to describe it. Really, what you do is you write a Lambda function. It's stateless JavaScript code that can perform some action. And then you can, once you've written the cloud function, you can go and subscribe it to services and have events from the services trigger a Lambda function to run. So let's think about our particular photo CMS example again here. Now, I can have push events, or I can have pull capabilities out of Lambda as well. And so in S3, you can actually set up an event. Hey, when a new image lands in this bucket, trigger the Lambda function. Send an event to the Lambda function, and then Lambda will do all the resizing. So now I don't have to manage the queue and manage the auto-scaling tier there. I can have Lambda do it. So sometimes queue with long polling might be the best answer. Sometimes Lambda might be the best answer. And further, I can have it pull out of DynamoDB streams and do things. I could have it go and check, verify an address when an address goes into a table in DynamoDB. I could have it pull from a Kinesis stream and take actions based upon something in the Kinesis stream. I can trigger events from SNS, all sorts of things. So lots of capabilities here in a bright future for Lambda. And it AWS manages deploying that JavaScript code on infrastructure and scaling it out for you. So, as requests come in, we scale out those JavaScript, little compartments that are going to do the work and shut down. So we manage the infrastructure. You don't really manage any infrastructure. You just say, I want to load this cloud function in JavaScript up to the cloud. So I guess the whole point to all this, right, is loose coupling sets you free. The more loosely coupled your services are together, the better you can scale. So design everything as a black box and independently, decouple the interactions, and favor services with built-in redundancy and scalability out of the box rather than reinventing the wheel and building your own. There might be a place for that, and we're going to talk about it coming up, but when you're starting out, man, use those services that are going to save a ton of time and effort. So now we're approaching 1 million plus users, and this is where we need to think a bit about all of the previous things we've done. So we might have been going multi-AZ. Maybe we want to introduce a third availability zone with an auto-scaling tier that's going out there, maybe more read replicas out there, another cache out there, so we can accommodate more users in that way. We always want to be load balancing between all our tiers to decouple those tiers so we're not having point-to-point connections between servers. Deploy service-oriented architecture as much as possible. Be serving all of our content out of S3 and CloudFront, caching off our database, separating session state from Dynamo. All those things are important here. And this is what our architecture starts to look like, right? So now we've got worker instances that are long polling out of SQS to do stuff that wasn't, that was originally part of our web instances. Now we've moved that out and we can scale that organically or independently, excuse me. We also have an internal app instance. Maybe I've got some web services running behind another load balancer, and maybe my app calls it. Maybe it's an API server for our mobile app. I don't know. But again, I've decoupled that particular component of my application. I also might have Dynamo and S3, being processed by Lambda functions that are running out there as well. I'm using SES to do all my transactional email. I'm calling that via API. Lastly, I'm front-ending my web stack with CloudFront, and I'm actually front-ending my static content with CloudFront as well, like we discussed before. You see how I'm doing on time. So what are the next big steps here that you want to take in your application? Well, as you're getting to 5 to 10 million users, this is where you might run into some database contention issues on writes. So how do you solve this? Well, we're using a relational database. We got some good patterns. And we're going to talk about federation and sharding, so let's dive right in. So what is federation? Well, really, it's where we're splitting up our database by function or purpose. So we just broke out our single database into a forums database, and a users database, and a products database. We might have many functions that can live independently of each other here, and so they're in different databases. But what do we lose here? Well, it's harder to do cross-functional queries or joins. Across these areas. What do you have to do? You got to do that through code, right? My app would have to query one of those databases, bring back the results, and then take those IDs and put them into another query over in the other database, or something like that, right? It adds a little bit of complexity, but it allows us to not have to shard for quite a long time. We can go pretty far here by federating and not having to shard, and we're going to talk about sharding next. So this isn't going to help with a single huge function or table, and that's where we get into sharding. So sharding is where I've got this single huge function or table, and it's running the bounds of my database, right? So I've got to do something with it. So now I'm going to carve it into multiple databases, and what I need to do is I need to write some logic into my application layer, or potentially use an ORM that's going to understand, hey, user A is in this database, user B is in this database, user C is in this database. And the easiest way to think of it, usually you separate these things by key space, and your ORM understands what keys go in which database. But if you want to think of this in its most simplest form, my users with the username that starts with A through L are in this database, M through S are in the second database, T through Z are in the third, right? That would be a very simple explanation of sharding. And really, there's no practical limit. I can keep on sharding as long as I'm using something to manage it smartly and manage my key space smartly. And you can do sharding on SQL or NoSQL. So this is what the people are doing with large Cassandra deployments as well, and large Mongo deployments. They're sharding their data across those. And this is what DynamoDB does on the back end for you. So you talk about scaling Dynamo up to 500,000 reads and writes per second. I mean, something's happening on the back end, right? You just don't know about it. We're managing it for you. We're managing that scaling out of that database infrastructure on the back end for you, so you can actually handle that amount of traffic. So as you crank that dial on Dynamo, things like this are happening on the back end. So maybe you want to move to NoSQL functionality here. It's similar in a sense to federation in that each table is like its own database, right? There's no relation between them. I can't do a cross-table query and join these tables together to grab results from both that meet some criteria, right? So I need to query a table, get back the results, and then query another table, and that's what happens with NoSQL. And that's why I said don't start with NoSQL. Start with SQL, because it gives you a lot of things out of the box that you don't get with NoSQL. But there are cases where this is what you need to do. If you start getting to web scale, there's definitely probably going to be a place for NoSQL. There might be a whole bunch of use cases for rapid ingest of data, like clickstream data, leaderboards, cart data, temporary data files, metadata lookup tables. There's a whole bunch of places where NoSQL is really great. Just make sure you're using it in the right spots. Okay, so a quick review. Multi-AZ your infrastructure, and make use of services that are designed out of the box to be scalable and fault tolerant, and you don't have to invent it yourself. Build in redundancy at every level of your application, like we've discussed. Like, definitely start with SQL. Even if you're going to move to NoSQL at some point, there's always a spot for SQL in almost every application I've ever seen. Cache data both inside and outside your infrastructure using the techniques we discussed. Use automation tools in your infrastructure. Make sure you're using metrics, monitoring, logging, to determine what changes you need to make, and make sure that application is well instrumented so you understand what changes need to be made to your infrastructure. Split out as many components as you can using SOA principles. Use auto-scaling once you're ready for it. Like I said, don't reinvent the wheel. Reuse those services that are out there for you, and only move to NoSQL once it makes sense. So putting this all together, you really can get to the point where you're talking about delivering a service to over 10 million users, and this could really scale like onward, to infinity and beyond. So you can iterate on top of these patterns and get to 100 million plus users here. So some of the things you might think about for going to that kind of scale: more fine-tuning of your application. We're using a lot of the techniques we talked about. More SOA. Break out every nook and cranny of your application into a separate component that can scale on its own. Maybe you were running multi-AZ, and you should still run multi-AZ, but maybe now you go to multi-region. And like a great example of that, like think about Amazon's latency-based routing. If you haven't heard of that, take a look at it. So what it does is it allows a DNS request to come in from a user, and latency-based routing says, where is the nearest Amazon region where that's running? And it'll route the traffic to the nearest region. And you could have an app stack running in multiple regions around the world that are close to your customers. Now, that adds other complexities, but if you're running at 100 million user scale, you've got the engineering force to figure that out. How you ship data around, how you keep things in sync, or how you redirect users back to other regions, all that kind of stuff, right? So this might be the spot where you want to start building custom solutions. Maybe these out-of-the-box solutions don't fit your needs at 100 million users, right? There might be some requirement or some nook and cranny that you can make better or squeeze some more performance out of by building it yourself, and you probably got a good engineering staff to do that. Lastly, just focus on deep analysis of your entire stack, figure out what you need to do and what makes sense. So next steps here would be, take a look at our documentation. If you haven't seen it, off of every page there's a documentation link off of every product page, but you can find all of them at aws.amazon.com/documentation. We have an architecture site that shows a lot of these patterns. There's also a place for startups if you want more information on startups. We have a free tier. Also, all this stuff will be on YouTube. So this talk will be on YouTube next week. I believe it's going to be posted along with these slides. Will be on SlideShare about a week out, so you can take a look for them there. Feel free to ask for help. We've got forums. We've got premium support. Or find an account manager and a solutions architect. And you can contact us if you don't have one today from the website. So thanks for listening. Really appreciate your time. What I think we're going to probably do, I think there's a couple SAs that I had join us here, and we're kind of at the end of the hour, so we're going to step to the back, and we'll answer questions while the next person is setting up here. So really wanted to thank you for listening. Also, inside of your application, there's the ability to rate this. Let me know, give me feedback. We want to get better, so thanks again for coming.